Hi all, I hope you guys are doing amazing. So we will see today's daily challenge on Leetcode and we will try to solve it together. So let's see the problem statement, what it wants us to do. So write an API that generate fancy sequences with append, add all and mult all operation. So we need to implement a fancy class which is nothing but a sequence of integers, okay? It stores and sequence of integers, and whenever initially that sequence will be empty, and whenever an append will be called, it'll append the integer value to the end of the sequence. And whenever this add all function will be called, it increments should increment all the existing values in the sequence. And whenever this mult all will be called, it should multiply all the existing values in the by an integer m, and get index idx gets the current value to at the index. Okay, so let's say what is the thing is, let's say you have this vector created. Whenever an append element will come, so let's say append of 10 came, okay, fancy dot append of 10, then you need to append this element to your vector. Okay, and let's say now something came which is add all 2. Okay, this type of function can also come. This was append function. Then you need to add 2 to each of the element. Okay, I mean, you should not exactly add or whatever, but it should be added. It should be stored as if it is added. Okay, and when mult all will come, let's say mult all by 2, it will be like something like this: 12, 16, 24. So we're multiplying all the elements by 2, and let's say you are now they want to uh, get this get index of idx. So they want to see that what element is there at in this index. Okay, so if they tell that get idx, okay, get index, and they pass 2, so it means that 0 1 2 at this index number 2 there is 12 now stored, so you need to return this 12. Okay, and these many function calls may be called one in a 5 number of times. It is given in the constraints. Okay, so yeah, one obvious brute force solution to this is that you store all the elements in the vector, and whenever this add all element is called, you just iterate through every element in the vector and add 2 to this. And whenever this mult all element is called, you iterate through all the elements in this vector and multiply by 2. I hope this greedy solution, this brute force solution, in fact, is very much obvious, and it for obvious reasons it gives you a TLE, because if each of this operation you take O of n amount of time, and you call all these n times, so your total results will be n O n square, and since n is 1e5, you cannot afford to do that. In fact, all of these functions you have to implement is in O of 1. Okay, all of these functions you need to implement in O of 1. Not even a single function can be O of n, because what if that function is called, let's say, n by 2 number of times out of total n operations, right? So then you will get O of n square by 2, something like this. So I hope you do understand that all of this you need to implement in O of 1. Okay. Now, proceeding, you will have some ideas like, uh, then definitely whenever add all will come, you do realize that whenever add all will come, we can't really add this 3 to every element. Okay, so what can we do? We store this 3 somewhere else, and whenever some you will want to return a particular index, you go to the index and apply that. Yes, we can definitely do that. Okay, so let's say you have a number a. Okay, you are first multiplying it by m1. Okay, and let's say you are incrementing it, then again you increment it by i1. Okay, now let's say this result you stored, right? And let's say again you are multiplying with m2, and again let's say you are incrementing by i2, something like that. Okay, so what will be the net result? So first time you did mult all. Okay, then you did add all, then you did mult all, then you did add all again. Okay, So yeah, it will be applied to each element, but every element. So, but for one element we are now discussing. You do realize that you can simplify this particular expression into something like this: m1 m2 plus I1 m2 plus I2. Okay. Now if you see, if I want to tell you that what will be, let's say you did all these operations, so instead of storing these operations or anything, you store that ultimately to a what you need to multiply, okay, to get something like this, and ultimately to b a what you need to add, uh, to get something like this. Okay, so first multiply and then add. So you do realize that the multiplication factor, so if you keep some global multiplier kind of thing, okay, global multiplier kind of thing, okay, that will nothing be but m1 m2. Okay, and if you keep some global adder kind of thing or global incrementer, in this case it will be I1 m2 plus I2. So one thing you do realize that whenever you want to, let's say now, multiply by m3, okay, you can have a global multiplier variable and multiply it by m3, okay, again. But if you are multiplying m3 to this whole number, okay, then you need to multiply this m3 also by global incrementer function also by m3. Why? Because when m2 was there, again you had only I1, but you multiplied this also. Not only to m1 you multiplied m2, to I1 also you multiplied m2. So therefore to global, whenever you are multiplying something, you will multiply this global multiplier as well as this global incrementer. But let's say you are only adding, then you only need to increment, let's say with I3, only need to increment this global incrementer. Okay, so now you might be thinking, hey, if I have at the end, now what I do, instead of storing all the operations, uh, I just have this global multiplier and global incrementer, which I keep on updating in every function call. Whenever they will give me an add all type of thing, I will, instead of updating all the elements, I will just update this global multiplier. And in the vector, let's say I have a 2, 3, and let's say a store over here and then 4. I will pick this a whenever, let's say it asked me to find what element is present at index number 2. Okay, so I will just pick this a. I will multiply with this global multiplier and I will add with the global adder. Okay. Now, but can you think of any issue with this method? So now you will tell that, hey, everything very easily we did. Okay, we can multiply and as well as add in O of one number of time. We can access this index as well as perform this whole thing in O of one number of time. Then what is the issue? What is the issue that is still remaining? Okay, let's understand very clearly our approach with another example. Okay, initially we have an empty sequence. Okay, let's say you, one function you did, what was that, you did something like append of 5. Okay, now your sequence has 5 in it. Now you do something like add all of 2. Now your sequence has what, 7 in it. Okay, now you have, let's say, something like append of 10. Okay, so you have something like 7 comma 10 in it. Now let's say you multiply it by 2, multiply all 2, so you need to multiply everything by 2, right? So you will have 14 and you will have 20 in it. Okay, okay, so now let's say you appended another element 15. Okay, let's append 15 to this. Now you have something like this: 14, 20, 50. Now this get index, this number can be called anywhere, right? Can be called anywhere. So it could have been called here, it could have been called here, or let's say after this it's called. Okay, so the thing is that for get index, let's say now you call something like get index of 2. What will you return? You will return 15. Okay, or but if you do get, now the thing is that you appended, what were the actual elements which you appended into your array? It was 5, it was 10, and it was 15. Now we just now told that we are doing a global multiplier and global adder. I am not modifying each element. Okay, I am not modifying each element because that will make me iterate the whole array. When in case of a long array, let's say multiplying by 2, it will make me iterate the whole array. So I will not just do that. Okay, I will keep a global multiplier and global adder. Okay, but you see, when you are asked to access this index number 2, you gave me answer as 15 only. Okay, but when you are asked to, let's say, access this index number 1, you will give me 10. You not give me 10, right? You will give me 20. Okay. In this case, you did not perform any operation because 15 was just now appended. In this case, you performed only multiplication by 2. The 10, you only multiplied it by 2 because it after appending 10, only this operation was done. Now for this 5, you see, you give me 15, not 14 and not 5. Why? Because after adding 5, you also added 2 and also multiplied by 2. Both these operations were done. Okay, that's why you do. But if you keep a single global multiplier or a single global adder, it will not tell you the information for every number, right? But then again, if you try to store a separate multiplier or separate adder for each and every element, that will also give you a TLE. Okay, that will also give you a TLE. You cannot do that. So what to do in such a case? Now, the thing is that I will have a global multiplier and global adder. Now I will do it with all the elements. Okay, blindly I will do it with all the elements. But there's a catch over here. Instead of storing a 15, whenever this append will be called, instead of storing a 15, I will store, can I store something else? So I know that my net resultant is that my global multiplier is 2, my global adder is 2 at this point. So whatever number I do, I will multiply that number by 2 and add that number by 2 and give me the answer, give the answer as a result. Okay, but whenever 15 was called, what I can do is that I can subtract a 2 from this. Okay, I can subtract 2 from this. Okay, see, uh, now see, you global add, whenever you do, you see, you multiplied it later, right? So the adder is actually 4 now. The adder is actually 4 because plus 2 was there. Now you I hope you do remember this, that way to the global incrementer also you need to multiply the multiplier. Okay, so initially the global incrementer was 2, but after multiplier came, the multiplier also multiplied this 4 also. Okay, 2 also to get 4. So one thing you can do is that instead of storing 15, you store 15 minus 4, that is 11. Okay, that is 11. And also you divide it by the 2 to get 5.5. So in the vector, you actually stored, instead of 15 in 15's place, you stored 5.5. Okay, now you see that your global multiplier is nothing but 2. When accessing the element, your global incrementer is nothing but 4. So what you can do, you can just multiply this by 2 and then just add 4 to this. You will get 15. So basically the idea is that since you need to do the global multiplication and global addition to each of the element at the final also, you do not store the actual element point while during the append. During the append, you store a modified element. Okay, so the amount which you are supposed to multiply, you divide that amount, and the amount which you are supposed to add, you subtract that amount. Okay, and then store the element. Okay, so whenever the thing is that, let's say the global multiplier is x and global adder is y. So when a value, let's say a, wants you to store append to the data structure, okay, then what you do, instead you know that this is the multiplier and this is the adder, right? So you do a minus y, okay, divided by x. You do this, you do a minus y divided by x, and then store it, into your vector. Therefore when the multiplier will be, whatever will be changed, whenever, if you want to do not perform, if you want to not perform any operation and then do it, okay, then what will you do? You will multiply it by x, okay, and then add by y. Multiply it by x and add by y will give you a again, okay. So that element at that point is preserved if you just store it. So, okay, so whenever a value will be asked to store, you will not store the actual value. Rather, you will use this global multiplier and global adder to subtract and divide, okay, to subtract and divide, and then store the subtracted divided value. Now, since there is a modulo operation, you can't really easily do the subtraction or division. You need to write this div mod function. I have told it multiple times in my video. So basically, when you are asked to do a plus b whole mod, what you do, right? You write a mod, a modulo mod, b modulo mod, and then again whole modulo mod, like this you do, right? But whenever for multiplying also, if you want to divide, you can do mod separately. Okay, you can do separately and at the end also do a mod. But for divide, when you are asked to calculate this, you cannot perform a whole modulo, right? You cannot just write a modulo and b modulo. Okay, you need to write another function div mod that will do it. Yeah, so we will talk about that. Meanwhile, let's try to write this function first of all. So at first, let's define hash define ll long long, okay, because we will be using this, and I will have some private variables. The first variable, as I told, is a global multiplier, okay, which is initially 1. Then I have a global incrementer, which is initially 0. So initially, I am multiplying by 1 and incrementing by 0. We should not initialize in private variables only, if you know. We should initialize in the constructor, okay? Anyway, so we have a vector of int, and this will be nothing but our whole vector only, okay? So no problem with this. In when the constructor is called, you initialize this global multiplier by 1, and you can also initialize this global incrementer by 0, okay? So yeah, after when you are trying to append something, what will you do? As I told you, uh, instead of appending this value directly to vector, you modify this value, okay? So let's do something like value equals to uh, value minus global incrementer. Now you need to perform a modulo mod, okay? Whole modulo. But I hope you know in my subtraction also you cannot just directly do modulo. So let's say you are doing a minus b whole mod, right? This is nothing but a minus b plus mod whole mod. Okay. Why? Because a minus b can be a negative number, and negative number you cannot divide it by anything, right? Do a modulos, and yeah, these are the basic operations. I have explained you multiple times also why this happen. You just add modulo and then do this a modulo, because modulo is nothing but 0 only, okay? If you divide this with the perform a distributive operation with each of them, it is nothing but that only, okay? So yeah, in order to get rid of the negative values, we do this. So global incrementer plus mod minus divided by mod, okay? And again, this value will be nothing but div mod of uh, value and global multiplier. Okay, so whenever you are storing, you first subtract the value and then also divide the value and then store it, okay? Then store it. Because when you will be getting the index at a particular point, you will be multiplying as well as adding, okay? So these two will definitely go hand in hand. And when you want to add all value, you can just increment the global incrementer, okay? So global incrementer. So let's have this as a long. And global incrementer also will be nothing but well incrementer plus this incrementer whole modulo, but let's make it long because the addition might result in a long integer, and then you are performing a mod. global, if you do some multiplier, that will be multiplied by m. Okay, so we have something like this: global multiplier will be multiplied by m. Okay, and global incrementer will also be multiplied by m. Okay, and the reason I have already explained you by some mathematics. Okay, so this will be modulo mod. Yeah. This is all. This is all. You see, a simple O of one operation. This div mod will give you O of log n operation. That much also you can do. We will write that and understand it later. Now get index at a particular index. Now in the question it is also told that if the index is greater than or equal to the length of the sequence, return -1. So you can just check if idx happens to be greater than or equals to wave dot size. Okay. Then you do return -1. Okay. And yeah, you just do this, and otherwise you have an answer which is nothing but vector at a particular index. Yeah, this is a zero-based index, so you do not need to do anything. You just access this element, and this value you subtracted and added, right? So here you need to just add, multiply, and then add. So answer will be nothing but answer into global multiplier, a whole modulo. But yeah, you need to write this long, and a whole modulo. Okay. If you just copy this, you also need the global incrementer. Just increment your value, and at the end you can simply return your answer. That will be all. That will be all. The only thing which remains now is writing the dmod function. You can also Google it on the internet. So basically, how do we do that? I am giving you a quick overview. It's not possible to completely explain, but yeah, this means nothing but you can write it in this way: a multiplied by 1 by b whole mod. This is nothing but doing a modulo mod and 1 by b modulo and a whole modulo. Okay, this is equivalent to this. Okay, you just divided the mod in between. Okay, yeah. After doing this, this is easy. This can be directly done. This can also be directly done. But the thing which cannot be done directly is 1 by b mod inverse. Okay, mod inverse. So we also call this mod inverse. So you can just Google it out how to find mod inverse. You will get using there is a proof using Fermat-Little's theorem. Okay, Fermat-Little theorem. There is some theorem which talks of some prime number. Okay, some properties of modulo with a prime number. So since this mod is also a prime number, which is 1e9 plus 7. Okay, the Fermat-Little theorem will apply to that, and that will be actually nothing but b to the power of md minus 2. Okay, actually by Fermat-Little theorem, this can be written as this. Okay, and a whole mod. Now this modulo is a very large number, right? It is 1e9 plus 7. Okay, so but b to the power 1e9 plus 5. How can you do this? This is a very large number, right? You need to multiply. If you are telling that I will just multiply b this many number of times, that will give you a TLE, because O of 1e9 does not work. You know that, right? This is a very large number. So when constant is O of 1e9, you cannot even do a linear operation. So yeah, time complexity always within 2e7 or 1e7 kind of thing you need to do in order to get accepted, in order to not get any TLE. So this can be done by binary exponentiation. Okay. Now a to the power e. So let's say if you want to calculate something like a to the power e and whole modulo, you can write a binary exponentiation function. So how does that work? Let's say you want to do something like 6 to the power 11. Okay, 11, if you try to write it in binary, what will be? It will be something like this. Okay, and you can iterate through every bits, and whenever you will get the set bit, okay, whenever you will get the set bit, you will update that power. Okay, so let's say your answer is initially 1, result is initially 1. This is giving you a set bit. Okay, so this will be nothing but 6 you are doing, right? 6, this is 6 square, 6 cube, 6 to the not like this, 6 4, 6 to the power 8. Okay, if you think it in this way, it is nothing but 6 to the power 2 to the power of I, something like that. Whenever there is I equals to, whenever there is a set bit, you need to multiply only those values. So you multiply 6 to the power 8, because there is a set bit over here. I hope you do understand this. There is a set bit, so you multiply 6 to the power 8. There is a set bit over here, so you multiply 6 square. There is a set bit over here also, so you multiply 6 to the power 1. So all these multipliers, what it does, it gives you the 6 to the power 11, which is initially, right? So this is known as binary exponentiation. Instead of doing a linear time over E, instead of O of E, your time complexity is nothing but O of log of E. Okay, because you are iterating through the bits of E, so your time complexity is O of log of E. So you can write this binary exponentiation function. So these are all commonly used function. Binary exponentiation, mod inverse, div mod, these are very commonly used function in any competitive programming. I have explained multiple times also. So this div mod will have something. So let's keep a mod also in global variable int mod. Let's call it 189 plus 7. And yeah, I was using this mod but not initialized it, so you can do that. And int, let's say I want to do, I want to calculate a to the power b. Okay, a to the power b. My result will be nothing but, as I told you, what did I tell? Div mod can be written in this way, right? So you can write it as a modulo mod multiplied by mod inverse of b. Modulo mod. Try this with long and whole modulo, right? Another whole mod. You can return this as your div mod. Okay. For mod inverse, you can write it something like this in v int md. Okay. Md is not required. What did I told you? According to Fermat reduced theorem, it will be b to the power md minus 2. Okay. So you can just return binary exponentiation of b and md minus 2. Okay. You can just simply return this. And yeah, again, one other function you need to write, binpow. So this is nothing but a to the power e you are calculating. E is the exponent which you want to calculate. Okay. And we have a result stored, result equal to 1. And while result greater than 0, I will iterate through the bits of the result, right? So I will left shift result in every operation by 1. Okay. Every time I will right shift this result by 1. And if I see this bit is set, so I will also have an a which will get multiplied. So a will be nothing but a into a, and this is nothing but long and whole mod. So what is this meaning? So every time I am squaring, multiplying a with itself. So 6 I am multiplying with itself. So 6 square, 6 power 4, 6 power 8. These things I am storing, okay, at every time in a only. And if in case the exponent not result greater than 0, I'm talking about the exponent, and if the last bit of the exponent is set, okay, if the ith bit is set, and I'm shifting every time by 1, so it means the last bit only is the ith bit over here. So if the ith bit is set, what you do, you multiply by result equal to result this, and you also have a long and also perform a whole modulo. In case of 0, whenever you get a bit is, whenever the bit is 0, you do not multiply it, and whenever the bit is high, you just multiply it. Okay, so by doing this, you easily get this 6 power 11. Yeah, it is as simple as that, and you can simply return result, right? I hope you got the result. And That's all with this problem. If you try to just submit it, uh, you should get an accepted. Let's see. Compile error, undeclared identifier M. So uh, where am I doing this? In line 44, uh, global multiplier. What did I do this? This is not required, right? What is this? This is not required at all. Only you need to multiply this answer globally and also add it and return the result. So what was that? I don't know. Okay, so we are getting a wrong answer over here. Let's try to see our approach in very detail. Bin pow is this, and div mod is nothing but mod inverse of B and multiplied by A. And whenever you want to append something, you call the global incrementer, subtract it, and divide also by mul. Okay, and for add all, you are incrementing only, and for multiplier, you are both increasing the global multiplier by M as well as the incrementer. And if this idx happens to be, you never appended this vector, right? So in append, you need to append also. You got the value, yeah. So you see, you got the value, but you never appended it. So yeah, just forgot to do that. Whatever value you got, you just append it quickly. So yeah, till we do have some wrong answer. So let's see what is the issue this time. We have this IDX, answer is vector of index. We did this multiply. So you have the global multiplier and incrementer. You first initialize them. This is the binary exponentiation function. You have e greater than 0. Okay, I wrote this function as only wrong. Exponent is the thing which you are moving, right? Yeah, need to be careful while doing this. Yeah, now we got the accepted thing. If you try to submit it for all cases, I hope it will work very fine, because every every function is being done in a very optimized manner, and you see you are doing pretty well in your global runtime as well as memory. Okay, so yeah, that is all. You are in the top branch. So that's all for this video. I hope you did understand. If you have any doubts, definitely ask me in the comment section. Yeah, that's all for this video. I will meet you in the next video. Till then, thanks a lot.